down into our notes. So what are we looking at here? We're looking at two-dimensional interference. And we said two-dimensional interference patterns, rather. And we said that sometimes this is called a double slit diffraction pattern. Okay, so why is it called a double slit diffraction pattern? Because when we saw this, we initially saw a barrier with two openings in it. We had our wave fronts coming in this way, boom. And so it was like having two sources here, source 1 and source 2, that the waves were emanating out from. Now, I'm not going to draw what we know happens. We know that we get a diffraction pattern on both sides of this that curved. I want to draw what we saw. We saw, instead of both sets of waves overlapping, all we saw was this central set of waves here that emanated out. We saw a line where there were no waves. Now, I'm exaggerating this for effect, folks, right? And then there was a line here of waves. There was a line here where we got waves as well, okay? And let's say there was a line here and a line here. This is not exactly what it looked like. In the video, we saw that the lines with no waves were a lot smaller than the lines with waves. This is just for sake of drawing, folks. So let's get some names down and talk about what's happening here. This here, we said where we saw the waves happen was an antinodal line. And an antinodal line is where we're getting max constructive interference. Okay? So at those points, we're getting maximum constructive interference. And so I'm going to call that A. Here is also a line, an antinodal line, right? A. And here's another antinodal line, A, antinodal line, A, and antinodal line, A. Now, just to do some naming here, this is called the principal antinodal line or principal maxima. Okay? Now, the way we denote that is we're going to call it A0. This here, 1 and 1, these are both called the first order maxima or the first order antinodal line. Okay, and I can name this exactly the same, and this is called A2, and I could label it here. I'm just going to label it here. This is the second order max or the second order antinodal line. Okay, that's just the way that these things have been named. We don't know why yet. We're getting the antinodal lines where we're getting them, but that's just where we're getting them. So now let's label the next thing. Here we go. Directly in between the antinodal lines, I'm getting here are nodal lines. Boom, and I'm doing those in green. So N, 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 right? So I'll write the notes for what N is here. This is called a nodal line. And at a nodal line, I'm getting complete destructive interference. Okay, so at every nodal line, you're getting complete destructive interference. Now, in terms of naming, I'm going to call this N1 and N1. This is N2 and N2. This N1 would be called the first order minima or the first order nodal line. Whereas this would be the second order nodal line or second order minima. Okay, that's just the way we refer to them. You'll notice there is no such thing in this picture as a principal nodal line. Why? Well, that has to do with a couple of things about this pattern that we need to mention. So first, that the principal antinode line here is along the bisector between the sources. Okay? Then we need to note that the pattern is symmetrical about the principal antinode line. Okay? So why is that true? A couple of caveats here. We will note that our two sources are in phase with each other and produce waves of equal wavelength, right? That this pattern would look very different if the two sources, like if they're tapping the water, they're doing it identically. This thing would look very different if they were completely out of phase. Take a guess. What do you think would happen if they were completely out of phase? If you said that the center becomes a nodal line and then everything where there's nodal lines become antinodal lines, so the pattern kind of like flips, you'd be right. So the principal antinodal line would be actually the principal nodal line, which is the bisector of the sources, if the waves were out of, or the sources were completely out of phase. We're not going to look at that. I just thought it was interesting to mention. And also, we're not going to look at what happens if the two sources were different frequencies and produce waves of different wavelengths. That gets really complicated really quickly, and it's outside of the scope of our discussion. Although, when we look at the mathematics of this, you would be able to derive it. Now, let's go to a couple of things that we saw change the pattern. So the first thing we saw that manipulated the pattern is changes in wavelength, right? And so I'll just write here small wavelength and large wavelength, right? Which is another way of saying high frequency and low frequency. But I will tell you it's really about wavelength, not about frequency here, okay? So if I have the same openings, okay, I just want to keep the patterns similar here. Okay, cool. With a small wavelength versus a large wavelength, hopefully what you remember is with the small wavelength, we had more antinodal lines. They were closer together, more nodal lines, and they were closer together. Okay. They still fanned out from the point in between, right? But what we had here is that the distance between adjacent nodal or antinodal lines got smaller, okay? Because we'll contrast that to with the large wavelength, what that looked like. Here, the distance between adjacent antinodal lines was quite large, right? The lines themselves were a lot thicker, and there were fewer of them, right? But small wavelengths, the distance between adjacent nodal or antinodal lines got smaller. So if I call the distance between adjacent nodal and antinodal lines, I don't know, x, right, as lambda decreased, x decreased. So we're going to see a direct relationship between those things, right? So like x would be from here to here or here to here or whatnot, okay? X would be from here to here. And we can talk about measuring x a little bit later. The other change that we saw was changes in D, and D is defined as the separation distance between the sources. Okay, and so here when we had D being reasonably small, and then I'll do one here where D was reasonably large, and then right here's D, here just our baseline picture. That's what we saw with a small separation distance. When the separation distance was large, we saw that there were more antinodal lines and they were all closer together. Okay, so I could keep drawing those, but why do it? I mean, the picture is not that great, right? Here, there's X. Here, there's X. So as D got larger, X got smaller, and yeah, that is going to be an inverse type relationship there. And we'll prove later in the course that it is actually an inverse relationship, right? So the one thing that we didn't investigate that theoretically we can is if it's a double slit diffraction rather than just 2 point sources tapping away, we could investigate the width of the slits, but I'm going to tell you I didn't do that until college level work. It does cause some slight weirdness in the pattern, but not enough. It's a second order effect, so we're going to kind of ignore that for now. So there you go. Those were our physical observations, right? We don't know why anything's happening. We just know that that is indeed what is happening in this. And so we need to know our patterns and our naming of our antinodal and nodal lines, our maximas and minima. So we're going to go back to the computer, start looking at the underlying architecture to this, and then come back to here to take some notes about that.